Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to discuss cold gas thruster. So let's dive right into it. Well, first we have to understand what the heck we are talking about, and we are talking about a subcategory of reaction control systems. So I already made a video about reaction control system, then I made about gyroscope. This is a subcategory inside reaction control system. It's not an independent system, it's just a subcategory of reaction control system. So it has same limitations as normal reaction control system. It also needs propellant. If you don't have propellant, it is not gonna work. So as simple as that. It works in space obviously, and it is very small and simple in terms of complexity. This is would be the simplest quote unquote rocket you can make. Is the simplest system out there. Now, how the heck does it work? Well, it has a few components. Like if you type on Wikipedia, you will find something simple like this. Basically, there is a tank and there is a nozzle. That's it. Of course, you will have a valve in between that you will control using computers, but everything else is super simple. You take high pressure source, whatever it may be. Generally, it is a tank which is pressurized with nitrogen, sometimes helium or sometimes neon if you want to do that. But generally, nitrogen and pressurized to ludicrously high pressure as long as the tank can withstand it. So generally 3000 to 10,000 psi depending on your design requirements. So you will have pressure source. That's part number one. Then you will have part number two, plumbing, basically valves and piping, because it's unlikely that you're gonna have the luxury of space like, okay, I'm gonna put the tank here and the nozzle will be directly in front. You may not have that luxury all the time. So plumbing and valve systems is there. Then you have the nozzle, same as any rocket engine. You have the nozzle fine-tuned for the altitude where you want it to work. And then you have to understand this one aspect. It has no chemical reaction. When I was talking about reaction control system, most of them are using some sort of peroxide, one variety or another variety. So all that is happening is there. Even if you take the liquid component, it does not have any energy. So you put it through a catalyst, you heat it up, whatever have you, you break it down. So during that quote-unquote breaking it down, you release chemical energy. That is the primary source of energy there. Now here there is no energy like that. It's just, it does not matter whether you have hydrogen, helium, whatever have you. The energy is coming from the pressure aspect. Basically, how much pressure do you have in the tank? Again, some gases are better at transferring pressure to actual kinetic motion, but you get the idea. There is no chemical involved here. There is no reaction. That is why it is called cold gas thrusters. So that's the whole science behind it. So are there any consequences of such a simplistic design? Well, yes, it has very low specific impulse. On top of that, it also has very low thrust. Now that is very important thing, because whenever you are talking about a rocket engine, let's say you are talking about space shuttle. Space shuttle had three main engines. Those were running on liquid hydrogen and oxygen. Ludicrously efficient, but idiotically underpowered. Again, they were powerful enough, but they could not get off the ground on their own. So they needed solid boosters. Solid booster, ludicrously inefficient, but powerful as hell. So generally, that is the trade-off in reality. You either get specific impulse or you get basically thrust. Generally, we try to get both, but you get the idea. So let's talk about ion engines. They have ludicrously weak thrusts. Basically, they have micronewtons. They are like weak, very weak. However, their specific impulse can go into 300 to 5,000 seconds. So you get the idea, like you get the mileage or you get the horsepower. Here you don't get anything. It's flat out weak. On top of that, in terms of, let's say you take ton, let's say you take a rocket and you're like, okay, how much ton the rocket is there and how much energy I can get out of the system. Basically mass efficiency in terms of like, okay, this was 100 kilogram, I got 500 kilograms of work. Awesome. Because again, you are getting chemical energy on a chemical system. Here you don't have such luxury. So in terms of mass, like however system you have to put on the top of rocket, you're not getting too much out of it. So it is very if inefficient in terms of mass. Basically you have to put 20 kilos just to get work of, let's say, 10 kilograms. So in terms of efficiency, it's low, inherently low. And to give you a simpler context, if you are using pressurized helium, best case scenario, best specific impulse you can get is 165 seconds, which is much lower than, this is like amateur grade rockets generally have higher specific impulse than that. And what if you are using cold gas thruster as Falcon 9, which is using nitrogen, you're gonna get 73. So you can understand, flat out, it's a very weak source material. On top of that, that's not enough. When you're talking about a rocket engine, you don't have to worry about fuel level. Basically, if you have 100% fuel, your rocket is going to produce, let's say, take a rough example, 10 tons of force. Awesome, no problem. Here's see, what will it do when it's 50%? It's still going to produce 10. What if it's going to do is like 45%? Again, it is 100% independent of the fuel. So it's going to produce the horsepower, whatever the torque it's supposed to produce, whatever amount of newtons it has to produce, it's going to produce no matter what you do, as long as there is fuel. Once you run out of fuel, then it's completely, then it's off. So here You don't have that same luxury. So you have a tank which is kind of again your main energy source, but it's deeply depreciating. So in the beginning your nozzles will be like producing let's say hundreds of newton. At the end of the once the pressure tank is like very low psi, you will be barely getting 10 to 20 psi. So you have to design a computer control that can handle that. And tank have to be over pressurized, so even at the end of your journey, let's say while you are landing this system, you still have enough pressure to get some things done. So that is the harsh reality of it. It's just flat out not a very efficient system. So that is if this had like even close to a normal RCS kind of thrust, basically Falcon 9 would not need grid fins. Flat out they will not need it. They will have the thrust, and thrust is like far more independent of aerodynamics, because again it is not independent of aerodynamics, it's just like less affected by it. You can get like much smoother landing, much gentler landing, much control in landing. You can't do that because even if you see during landing in space, the thrusters are doing all the j's. The moment it touches the atmosphere, the grid fin takes over. So that is the reality of it. It is not powerful. Flat out it's not powerful, nor it's efficient. So then why do we use it? If it's such a weak element, why the heck do we use it? Well, it's one of the simplest system. Even when you are talking about reaction control system, when you are talking about peroxide, where you have only one fuel tank, you have to consider heat output. That is why these systems are called cold. The heat is not something like, oh, it's 1 degree hotter or 50 degree hotter. It's like hundreds of degrees Celsius. So even if like you have just a fuel tank, a valve, a nozzle, basically engine chamber and nozzle, basically the chamber gets ludicrously hot. On top of that, the chamber generally has some catalyst, electrical heating elements, extra things, and you have to take into consideration. On top of that, you also have to make sure that the thing remains cool, because in space radiating heat away is a very serious consideration. So that becomes an extra system that you have to worry about. This system makes that system look like a much more complicated scenario. So basically liquid fueled rocket engine, primary engine is complexity is let's say 100. So when you come to reaction control systems, the complexity drops down to 50. When it comes to cold gas thruster, the complexity drops down to 20. So it is the most simplest system we can think of. So that is one primary advantage, is simple. Now again, simple does not mean anything if it has no use. Well, it has the advantage of being clean and safe. Think of it this way. When you're talking about astronauts have spacesuit once they go outside of International Space Station, but all the system of the spacesuit must be safe because it's generally parked inside the space station. So let's say they are using peroxide fuel tanks, something happens. So let's say a micrometeorite damages it bursts inside the ISS, is gonna destroy the ISS. So having nitrogen there, again, it's still dangerous, but it's much more like, if dangerous level is in peroxide tank would be 100, this will be barely 15. So that is it's clean and safe even in a worst case scenario. And it's not only clean and safe for the people, it's also safe for whoever landing crew is taking care of the rocket. Basically, if you have peroxide, you have to vent the system. You can see that whenever a space shuttle lands, like there were like multiple crew going there just to make sure the vehicle is quote unquote safe, because peroxides are not something basically lovely, they are very nasty. So that is the reason, clean and safe. On top of that, the exhaust is non-destructive. Think of it this way. Let's say ISS is in very low Earth orbit, and you have a lot of satellites that are very orbiting in low Earth orbit. Every one of them started to use exhaust, let's say peroxide exhaust. There will be so much dust cloud that will corrode the solar panels. Basically, like again, it will be like a space weather we have to worry about. And again, even if astronauts are using it, which is so close to these things, and maybe they are just working on the panel itself to repair it or to inspect it, their exhaust itself will damage the panel. You don't want that. Nitrogen will just push it, and again, on a molecular level it's inert, so it's not going to do anything serious. So that is why I use it. It's ludicrously simple. Like in terms of simplicity, it's like as simple as you can get, and it's clean and safe. Basically, even if somebody fires the exhaust right at your face, it's not going to burn it off. You're just going to be pushed back because it does not have too much thrust. And it's non-destructive. So again, even if tank ruptures happen inside the ISS, it's not gonna annihilate it. So we like it. So what can we expect in the future? Well, one simple thing, it is a simple system, so we want to miniaturize it. As of now, this is the smallest structure that we have figured out. Basically, yes, this is in palm of your hand, there will be nozzle and the valve. So it's quite small structure, and we want to use that in CubeSats. Now these are the CubeSat that is right now in space, and they are built by NASA and some Seeking technology. So the idea is the whole system is 3D printed here, again, except the tank and the plumbing and the valve system is 3D printed. The benefit of that is that this will give you very high high efficiency, relatively speaking, and it will allow like this sort of satellite to act as a external eyes. Basically, they can go outside of ISS and observe, rotate, and do a whole kind of analysis. And in future, this should help us to basically deorbit basically junk satellites and all that. And not to mention, cube satellites will kill for this kind of technology. Again, this is early stage. Once we can miniaturize it even further, because you have to know this is a 3U satellite. 1U is 10 centimeter cube. This is 3U, 10 centimeter by 10 centimeter by 30 centimeter. If you can make a propulsion unit that is, let's say, half U, basically you just take 10 centimeter by 10 centimeter and the half U, and it can work for long enough time. Let's say it can work for 1 year or 2 years. Again, the whole market of CubeSats will explode if you can do that, because right now CubeSats are just like use and throw. Many people are trying to do multiple things to make sure they last longer, because again their equipments are generally functional, but again it simply does not last. If you can make something simple, again cold gas thrusters, and you can make sure it lasts there for, let's say, instead of falling over in 1 and 2 years, it falls over like 3 to 5 years, the whole CubeSat market will explode. They will give you, like, take my money if you can develop something like that. So there is a lot of incentive to miniaturize the system. Now that's what's happening right now. There is another aspect that is happening in the labs. Basically, we want to create stronger and better tanks. If you have a tank that is like capable of 200 psi, that's it. That's your maximum limit, because there is no chemical energy, and that is your maximum that you're gonna get. And again, everything leaks over time. Everything leaks. So 200 psi. If you started with that, you're not gonna go very far. Let's say you started with 3000 psi. Now you're talking. Now you're gonna go. You can do some things. What if we went to 50,000 psi? Or 800,000 psi or something ludicrous like that? Again, if BFR, like basically, let's say BFR reached that point, it will simply not need grid fences. Like, bro, I got this. The thrusters is like, bro, I got this. You don't even need to worry. Again, you have to recharge it with liquid nitrogen, but it can take care of the situation. So we want to make the tank. How can we make tank stronger? Again, if graphene ever works out and we can truly make sheets of graphene, I'm not talking particles or powder or things like that, no, proper sheets of it, and we wrap it instead of carbon fiber, we just take a normal whatever, aluminum or something like, or heck, we may not even need that. If you can make a true sheets of graphene, you can just wrap it around itself and it's 100% impervious to everything. Again, you can have a tank that can hold 80,000 psi or 90,000 psi, and that point your psi would be limited by the valve design and the plumbing, not by the tank itself. So tank could have ludicrously high pressure. So these are the two avenues that a lot of people are working on right now. First avenue, miniaturizing it so CubeSats can utilize it, and then second avenue is making the tanks YOLO. So this was my presentation on cold gas thrusters. I hope you liked it, learned from it. In that case, please click like button, share it amongst your friends. That would truly help me out. And if you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment. Please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.